So, hello everyone. I hope you are doing good, and you must have gone through week 2 lectures as well. And I guess the previous live session would have been useful to you, and you must have been able to solve the some of the problems from your assignment. So, today we are going to build upon the problems we solved in the previous live session. So, today I will start with some theoretical questions itself so that you all can participate via chat or via unmuting yourself. So, for that, I was looking for some more people to join, but since it's already 3:01, I guess that we should start this session and let other people join in the meantime. So, let's start today's session. And as you all know, let me take my pencil. As you all know, that this course is being taught by our professor Sanjeev Samavan, and this course on semiconductor device. This is a course on semiconductor device and circuits, and I am one of the teaching assistants who will be solving the problems during the live sessions. And I hope that you are enjoying the other sessions as well. So, as mentioned in the previous lecture as well, this is my email ID. If you have any query regarding any question, you can drop an email and I will be happy to respond to your query, provided the question is not from the current assignment. If the question is from the current assignment, then I may not be able to solve it directly, but I will try to provide some hints to you so that you are able to solve the problems on your own side. And once the assignment deadline is over, we can solve the problem which you might be having doubts. and you just have to ping me via an email so that we can solve the problem. Okay, so let's move towards. Let me turn off the video so that the bandwidth is preserved. Okay, so that there is no issue with the internet connectivity. And now uh, there is a problem statement over here. It says that the wave function of the particle must be normalizable. So I would like someone among you to answer this problem so that uh, we will just have some understanding from your side how much you have been able to grasp from the lectures and how much you have been able to grasp from the previous TA sessions. So you can type in the chat whatever option you feel is the correct. I will not ask you for the reasons, but if you feel uh, any option among these four is correct, uh, you should try to answer that. I'm not going to force anyone to answer, but if you are willing to answer, you can unmute or you can type in the chat. Let me check the chat. Okay, I guess there is no response from our side. So let me do it myself. And it says that the wave function of the particle must be normalizable. So what does this mean? Uh, this is simply that there should be some finite probability of finding the particle in the entire space. As you have seen, when we said that this is the probability of finding the particle, this psi x was the mathematical, you can say, modeling parameter which helped us to model the a particle like an electron. Okay, so we said that we will model it using this psi, which is known by the name of wave function, and this wave function will have some property, and one of the property was that it should have some finite probability to be present over the whole space. So this is the condition on psi, that psi into psi star over the, for example, if we are considering 1D case, or the whole space has to be equal to 1. So let me write it like this: the total probability of finding the particle over the entire space has to be equal to 1. So from this we can easily say the option C must match, because the particle has to be present over some space. And for the normalization constant, whenever we try to find the normalization constant, we just said that it would be sum, if psi is some a times some f of x. Okay, if psi is some f of x, then we used to find this by just saying fx star into fx dx minus infinity to infinity is equal to 1, and this is the normalization constant that we found out in one of the previous problems. So let me wait a second. So let me, okay, sorry. So let me enclose it. I guess it is showing up correctly. Okay, let me enclose this over here, and let me write it again because there was some glitch. So it is minus infinity to infinity f of x star into f of x dx has to be equal to 1. So this was the normalization constant we were looking for. Now, moving towards another problem, which says that we have to mm, look into the four graphs for psi x, where the psi x has to satisfy, it has to be a valid quantum mechanical wave function. So you can type in the chat if you know, or if you want to participate in the problem solving. So if you feel that any option is not valid quantum mechanical wave function, you can type in the chat, so that uh, otherwise I will solve it from my side. So this is basically, you must have gone through the lectures where you have seen that the wave function has to satisfy some property, that it has to be continuous. Okay, so which function among these four is not continuous? You must look among these four which is not continuous. And I guess there is no response from your side. So as you can see, option A is continuous, but as you can see, option absolutely correct. Vabao, thank you. So as Vabao rightly pointed out, that this option D, it's not continuous at x equal to 0. There is a discontinuity at x equal to 0. So this is an invalid quantum mechanical wave function. So let's write it like this: psi must be continuous. Okay. So since 4 has discontinuity at x equal to 0, so we will say that this is not a valid quantum mechanical wave function. And also you must have seen that the derivative of the wave function, there are some properties, and one among those was that derivative should also be continuous. Okay, you must have gone through those slides and through those lecture content which professor taught. So now moving on to another problem, which is about the, you can say, the intensity patterns. Okay, so it says that we have the ratio of the maximum intensities. The ratio is given to be equal to 25 is to 1. Okay, and we have to find the amplitude of the ratio of the amplitude of the interfering waves. Okay, now we can clearly say that this, if there are two waves, the net intensity is given by a1 square. This is the amplitude of first wave, a2 square plus 2 times a1 a2 cos of phi. Okay, now depending upon this phase, we will be having maximum and minimum intensity. Okay, so the maximum intensity will be at phi equal to 0. Okay, we'll be having maximum intensity. Okay, and for phi equal to 180 degree, when we have this cos phi to be equal to -1, we will be having minimum intensity. And thus we can write the maximum intensity to be equal to a1 square plus a2 square plus a1 a2, and this is cos of 0 is 1, so it is simply a1 plus a2 whole square. So for I min, we can simply say it is A1 squared plus A2 squared plus 2 times A1 A2 into cos of 180 degree is simply minus 1. So it is simply, I mean, is simply A1 square plus A2 square minus 2 times A1 A2, or simply it is A1 minus A2 whole square. So this is the minimum intensity. So the ratio of the Imax by Imin is simply, let's go to the previous slide. This is the maximum value, A1 plus A2 whole squared, and this is the minimum value, A1 minus A2 whole square. Okay, so the ratio has to be equal to 25 is to 1. Okay, so it has to be equal to 25 is to 1 is A1 plus A2 whole squared divided by A1 minus A2 whole square. So it is simply 5 by 1 equal to A1 plus A2 divided by A1 minus A2. So it's simply 5 times A1. Sorry, there is some issue from my side. So it is 5 times A1 minus 5 times A2 is simply A1 plus A2 is simply 4 times A1 is 6 times A2, or simply it is A1 by A2 is equal to 3 by 2 is equal to 1.5. So from this you can clearly see the option B is matching with our answer. So we will select this option. Now moving towards another problem, which says that this is also associated with the wavelength, and it says that when we are using this electron beam lithography and we have exposed it to the electrons, and the wavelength of electrons helps us to achieve the feature size. So the feature size is of the order of nanometers, and we have used an electron gun for this, and this electron gun is having an energy of 50 kilo electron volts. Okay, and we have to find the wavelength of these electrons, assuming the mass of the electron is 9.109 into 10 to the power of, it should be power of 10 to the power of minus 31 kg, and the Planck's constant is given to be equal to 6.626 into 10 to the power of minus 34. It should be raised, and we have to neglect the relativistic effects. So let's not go into those relativistic effects, and let's just simply say the energy over here. So the energy over here is simply given by the kinetic energy, which is P square by 2m, and we know the momentum is given by h by lambda, where h is the Planck's constant and lambda is the wavelength. So if we substitute this in E, we will simply get h square by 2m lambda square, and or simply from this lambda will be given by h by 2m E under root. Okay, yes, it's good. Fine. So the lambda is simply 6.626 into 10 to the power of minus 34 joule second divided by root of 2. M is the effective mass, which is the rest electron mass, which is 9.109 into 10 to the power of minus 31, okay, into 50 kilo electron volts. So since we are dealing in the SI units, electron volt will mean 50 into 10 to the power 3 is kilo, and electron volt is simply 1.6 into 10 to the power of minus 90. So let's solve for this. Let's solve for this. It is simply 2 into 9.109 into 5 into 1.6, which is simply coming out to be 145.744, and this will be 10 to the power of minus 46. So let me write it like this. It is 6.626 into 10 to the power of minus 34 divided by its under root will be 12.072 into 10 to the power of minus 23. Okay, now let us divide these two. 6.626 by 12.072. It's 0.55 into 10 to the power of minus 11. Okay, so let's insert some slides. Okay, so it is coming out to be equal to 0.55 into 10 to the power of minus 11 meters, or simply second, or simply it comes out to be equal to 0.0055 nanometers, because the answer, the option is in nanometers. So the option D is the required option. So this much amount of wavelength of electrons is required in order to achieve the uh, this to achieve this kind of a feature size for this EBL process, electron beam lithography. Okay, for this problem. Now moving to another problem which is related to this one-dimensional potential well, where you must have seen in the lectures how professor solved for the energy for the one-dimensional infinite potential well, and the energy in the nth state, energy in the nth state En was simply n square pi square h bar square by 2m L square. So as you can clearly see over here, as the L grows, as the L increases, the En value decreases. Okay. So as L tends to infinity, En tends to 0. So this is one way of saying that the spacing between, let's say, infinity energy level at infinity and infinity minus 1 is almost negligible. So they will appear to be continuous. Okay, quasi, we can say they are uh, not quasi continuous. We will say they are almost continuous. Okay, so the this is the energy in the nth state. So for, you can say the energy in the nth state is given by this for an infinite potential well problem, and this now this electron will jump. It will jump from n equal to 4 energy level to the ground state energy level. Can anyone among you tell me what would be the ground state energy level? Would it be n equal to 1 or n equal to 0? Okay, so basically it will be n equal to 1, but you should find it why it's n equal to 1. Okay, there is some function which we found out at that time. We said that psi is not equal to 0 inside the box. So there is a hint for you that psi has to be some particular value inside the box, inside the infinite potential well box. So you must look into that, and I will just state over here that for ground state for this infinite potential well problem. Okay, n is equal to 1. Okay, so it jumps from n equal to 4. N equal to 4 is simply 4 square pi square h bar square by 2ml square, and ground state energy is E1 simply equal to pi square h bar square by 2ml square. Okay, so when there is this can say transition from the n equal to 4 level to the ground state energy level, obviously there will be some release of the energy, and it 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 is in the form of the emission of the photon, and the photon has some wavelength which is of the order of nanometers, which is 20.9 nanometer, and from this information we are required to find the width of this well, width of this infinite potential well. So we have been given these elementary constant values like the electron mass and the Planck's constant and the speed of light. Okay, so what we are going to do now is we are going to say that there is a transition from the n equal to 4 energy level to the ground state energy level, and as a result of this thing we will be having some emission of photons of a particular wavelength. So simply this energy which will be released will be simply given by E4 minus E1, which is the energy in the uh, uh, higher level, which is n equal to 4 and the energy in the ground state level. Okay, which is simply now pi square h bar square 4 square minus 1 divided by 2m l square, which is simply 16 minus 1 is 15 pi square h bar square by 2m l square. So this is the difference in the energy when we transition from the states. Okay, now we know that now this energy it has some wavelength associated to it. So we will write it like this, that energy is released in terms of photons. So this delta E is simply given by h nu. Nu is the frequency, okay, or h c by lambda, because we know this wavelength, and the c is the speed of the light, which is one of the elementary constants. So we can equate these values, which is this hc by lambda, to be equal to delta E. Delta E came out to be equal to 15 pi square h bar square, 15 pi square h bar square by 2ml square, I guess. Let me check once. Okay, by 2ml square. So this is what it is. This is equal to h by 2 pi. So let's cancel this h bar with this thing. We know that this is simply equal to 15 pi square. H bar is h by 2 pi. Okay, so it is simply h square by 4 pi square, and this whole thing divided by 2ml square, hc by lambda. Okay, this h and this h will go, this pi square will go with this pi square, and we have to find this L value. Okay, we will be left with c by lambda is simply equal to 15 by 8 h by ml square, or simply, this is not 18, this is 8, 15 by 8, yes, 15 by 8. So it is simply equal to, L is simply equal to 15 times lambda times h, okay, divided by 8m into c. This is what it is. Now let's plug in the values for these. Let's insert some slides first. Okay, so the L is 15 times lambda. Lambda was, I guess, 20 something, sorry, 20.9 nanometer. It is 20, sorry, 0.9 into 10 to the power of minus 9 meter, okay, into h is the Planck's constant, 6.626 into 10 to the power of minus 34 joule second, divided by 8m into c. 8 into m is 9.11 into 10 to the power of minus 31, and c is 3 into 10 to the power of 8 meter per second. So if we solve for this, let's solve for this, and this is simply 15 into 20.9 into 6.626 divided by 8 divided by 3. It is 9.5007 into 10 to the power of minus 20. So if I take its square root, it will be 3.08 into 10 to the power of minus 10 in SI units, which is meter. So this is the length of the infinite potential valve box. Okay, the answer has to be in the nanometers. Okay, the answer has to be in the nanometers. So it is simply 0.0308 nanometer. So this is the value of the L. This is L, not H. L. So the option, I guess the option B is 0.0308. So this is the correct option to go with. Now I have another problem about these wave functions where we have to find this normalization constant. So this normalization constant is simply given by uh, this wave function is given by this psi of x. This psi of x is the wave function, which is 0 for x less than 0, and it has some value. It has some value a times root of 30x L minus x when x is between 0 to L, and rest it is 0 for x greater than L. Now we know that there has to be some finite probability of finding the particle over the whole space, and that probability has to be equal to 1. We will simply say that minus infinity to infinity psi of x star into x is equal to 1, and it simply means, since this function has this definition between which is non-zero between 0 to L, so it is simply, the limits will simply be 0 to L. A star is simply a times root of 30x L minus x, and this has to be multiplied with psi, and psi is the same thing. Okay, and psi is the same thing, it is a root 30 x root of L minus x. Okay, so it is simply, this term has to be equal to 1, or simply it is just the square, it is a square 30 x square L minus x square dx, it has to be equal to 1 between the limits of 0 to L. Okay, so taking the constants outside the integral, 30a square is simply 0 to L x square L minus x whole square dx equal to 1. Now Again we have to integrate this thing, and let's just do it. Okay, so let me integrate this thing using this UV rule. So it is simply 30a square. It is okay, it has to be x square, L minus x cube by 3 with a minus, okay, with limits 0 to plus. This has to be differentiated once. X square, it is 2x now. It is 2. Actually, it has to be minus over here, okay. So minus 2 by 3, 0 to L, x, L minus x cube, and there will be a minus of this thing which will make this plus, and this will be dx equal to 1, okay. This is the whole thing. It is x times L minus x. Now putting the limits over here for this thing, let's put the limits first so that we don't get confused. It is simply 30 times a square for x equal to 0 and x equal to L. For both these values, you can clearly see that this part of this integral will become 0. Simply, when we put x equal to L, the first term will be L minus x will be L minus L, and it will go to 0. And then we have this, what you can say, this at x equal to 0, it is 0 times L minus 0, which is itself 0. So this whole thing will go, okay. This is equal to 0. And now we have this thing 2 by 3. It is simply 2 by 3 x times L minus x to the power of 4 by 4, and for this we will be having minus because it's L minus x, okay. So it is minus times this thing 2 by 3, okay, 0 to L, plus integrating the same thing. I have written plus directly over here because I know the minus will come from this, and minus will be plus. So it will be 0 to L minus x to the power of 4. I have to differentiate this x. It will be this thing, x equal to 1. This is whole multiplied by this 30a square. And this thing again is equal to 0. Absolutely. For x equal to L, this term is 0, and for x equal to 0, this term is 0, making this whole term to be equal to 0. Okay. Now we have this term only, which is 30a square, which says that L minus x, it is simply minus times L minus x to the power of 5 by 5 into 4 will be simply 20, with limits between 0 to L, okay. So is equal to 1. So at x equal to L, this is 0, and at x equal to 0, it is simply 30a square. Minus and minus will become plus. L to the power of 5 divided by 20 is equal to 1. This thing will go. Okay. Sorry, have I forgot something? Okay, this is what I forgot over here. Since it had this 2 by 3, I multiplied this 2 by 3 over here, and I didn't multiply it over here. So I have to multiply this 2 by 3 with the whole thing, and this has to be 2 by 3 over here as well. Absolutely, because we are solving this integral. Okay, this is the integral we are solving. So 2 by 3 times 30a square. Okay, so this 0 and 0 will go, 2 and 2 will go, 3 and 3 will go. It is simply a square is equal to 1 by L to the power of 5, or simply
A is equal to L to the power of minus 5 by 2, or A is equal to L to the power of minus 2.5. Okay, so from this minus 2.5, wait a second. Okay, so this is our answer, which is minus 5 by 2, okay, or minus 2.5. From this we can clearly say the option A is matching our solution, and we will be going with this option itself. Now moving towards another problem, which is also related to this infinite potential well, where this infinite potential well will be having some L equal to this 7.3 nanometer along x-axis. Since this is an infinite potential well in 1D, we can clearly say that this L is equal to 7.3 nanometers, and the system is in energy state n equal to 3. Okay, so we have to find the probability uh, of finding the electron per length, per nanometer length, at some x equal to zero point 0.3. So we know the wave function for this infinite potential well. Let's write it down. The nth wave function is given by psi n of x to be equal to, where this is a normalization constant, root 2 by L, sine of n pi by L. L is the width of the box and x is the position. Okay, now the probability is simply given by psi into psi star. I'm not saying the whole probability of finding the particle in the whole space, but I'm trying to find it now at a particular point. So the probability of finding an electron per unit length, let's not write it per unit length over here. Let's write simply probability of finding an electron is simply given by psi star into psi. Since this is a real function, it is simply psi mod sin x whole square. It will be simply 2 by L root 2 by L whole square, and root 2 by L whole square will simply be 2 by L. This will be sine square n pi by L x. Okay, so this is the value of this. Now let's put the values. It is simply 2 by L. L is 7.3 nanometers, 10 to the power of minus 9. Sine of n is 3 pi by L, and x is 0.03. It is simply, sorry, L is 7.3 into 10 to the power of minus 9 into x is 0.03 into 10 to the power of minus 9. So this 10 to the power of minus 9 will go with this thing, and we will be having some value for this, and let's just directly calculate it. So we have to find it per nanometer. Since we have to find it per nanometer, we can take off this 10 to the power of minus 9. We can cross over this. You can say that this nanometer will go with the nanometer, and we will be simply left with 2 by 7.3 per unit length. So this is per unit length, probability per unit length is 7.2 sine square. Let me calculate the value of this thing. It is 3 into 3 is 0.9. 0.9 divided by 7.3. 0.9 divided by 7.3. 3, it is 0.123 pi. Sine square of 0.123 pi is simply coming out to be equal to 0.142, and 0.142 into 2 divided by 7.3 is simply 0.39. Okay, so it's coming out to be equal to 0.039, 0.0389. So it is 0.123 pi. It is coming out to be equal to 0.0389. Okay, so the option A is the closest. So option A is the closest to our answer, and as a result of this thing, we will be having we will select this seventh for the seventh question. We'll select option A. Now moving towards another problem, which is associated with the electrons which are being pushed through, or which are being to fall through a pair of slits. Okay, wait a second. So the electrons are accelerated through an electric potential, which is given by this V value, and they are allowed to fall. They are allowed to fall through a pair of slits. Okay, and these slits have a separation of approximately, it is given to be equal to 100 nanometers, and we are recording its interference patterns on some recording screen. We are recording the pattern of these electrons, and it is found out that the wavelength is equal to 1 nanometer. So we have been told to find the value of this electric potential V, and we have to also find the what is the minimum spread in the electrons momentum when they are allowed to fall from these pair of slits. Then the separation between these two slits is 100 nanometers. So we have been given the value of the delta x over here, and we have to find the value of the delta v. Now from this, first of all, we have to use the energy balance. What we are giving some electric potential. Electric potential is q times v, because we are equating energies. V is the potential. If we are just using the energy and potential interchangeably, then we have to multiply this q, this potential, with v in order to get the energy, because energy is electron volts, and v is volt itself, and this q multiplied by with this v is simply electron volt, and this is qv is simply equal to p square by 2m. What we have done, we have simply used energy balance. Okay, we have simply used the energy balance for this problem. Now this p square by 2m, but we also know that this p is given by h by lambda. Why are we after this lambda? Because we have been given this to be equal to 1 nanometer. So this q times v is simply given by h square by 2m lambda square. Or simply, let's move to another slide. Okay, so v is given by h square by 2m lambda square q. V is given by h square by 2m lambda square q. It is simply 6.626 into 10 to the power of minus 34 whole squared divided by 2. M is 9.1, but let's check what they have taken. Yes, it is 9.11. It is 9.11 into 10 to the power of minus 31. Lambda is, I guess it was 1 nanometer, so it is 10 to the power of minus 9 nanometer whole, which is this 10 to the power of minus 9 is the 1 nanometer whole squared into Q. Q is the electronic charge, which is 1.6 into 10 to the power of minus 19. Now, let's solve for this. Let's solve for this. It's 6.626 whole square, 6.626, 43.09, 43.908, 2 into 9.1, 6, 29.152. So V comes out to be equal to 1.506 volts. So this is the value of the potential, electric potential, that we are going to give to these electrons. So this is the part A of this problem. Okay, so I guess one part we have found out to be equal to 1.5 volts approximately. So these two options are gone, and we are left with now C and D only. For D, what we are going to find? We are going to find the minimum spread in the electron's momentum. Okay, so this will be simply given by the Heisenberg's uncertainty principle. This is this delta x, which is a separation, which is 100 nanometer. So we can say that if we use the, for part 2, we use this Heisenberg's uncertainty principle, where simply delta p in direction x into delta x has to be greater or equal to h bar by 2 pi. Sorry, h bar by 2, not h by 2 pi. So h by 2 pi and h bar uh, by 2, they are equivalent things. So this is the uncertainty in the measurement of the position, and the uncertainty in the measurement of the momentum, which professor taught in the lecture. I guess it was in the week 1, where he told that both the quantities cannot be measured simultaneously, and he gave the example of the uh, analogous example of an, let's say that mass, the string example, where we are having the frequency. When we know the frequency of the signal, we cannot tell where exactly a signal is, and when we know the position, or the, for example, I'm having a string or a rope in my hand, and I just give it give it I get just pull it like what we do, and there will be a hump in it once, and we can say that the particle is localized, or the rope has having a hump at this x equal to, say, let x equal to 0, and after that the rope is flat over the whole space, and thus we can say the particle or the rope is present, its hump is present over this place, but we cannot comment about its frequency. So that's what professor was saying in the slides. He simply said that these two quantities, which are the momentum and the position, they cannot be measured without having zero uncertainty between them. If we measure one thing, then there will be an uncertainty associated with the other thing. So it is simply now this delta px is the uncertainty in momentum. If we exactly know the this uncertainty in, or the separation between these slits, we can say this is h bar by 2 times this delta x, and this h bar is simply 6.626 into 10 to the power of minus 34, and I guess delta x was 100 nanometer. Yes, it is 100 nanometer. It is 2 pi because h bar is h by pi into, okay, h bar is 2, h by 2 pi, h bar is h by 2 pi, so it is 2 times. Now this delta x is 100 nanometer. So now let's solve for this. It will simply be this delta p x has to be greater than this value, which comes out to be equal to, let me solve it, 6.626 into 5.27, 5.27, 5.27, 10 to the power of minus 28 kg meter second. Okay, so from this, what we have got this to be equal to greater than this value. Okay, so if it is greater than this value, it means that uh, this option is also not valid, and we will have to select this option D. Okay, we will go with this option D. This is the correct one to go with. Now, moving to another problem, which says that the wave function of a particle uh, at nth state is given by psi of x equal to root 3 cos of 2 pi x by a, which is between the limits of mod x less than a by 2, and for mod x greater than a by 2, we will be having this to be equal to 0. So let's write it down like this. So what we have to find out, we have to find out the average momentum of the particle in the nth state. So the average momentum delta px is simply given by minus infinity to infinity psi of x star, where this p of x is the momentum operator now. Okay, as we know, we have seen this thing, we when we did solve the problems in the previous session, we said the expectation value is given by of any operator of anything is given by this formula, which is psi star times the operator which will operate on the psi, it's and this has to be integrated over the whole space. Now this psi of x is defined such that it has a value of root 3 cos of 2 pi by ax for x less or equal to a by minus a by 2. Okay, and it's 0 otherwise. Now it simply means that this delta px is simply given by minus a by 2 plus a by 2 root 3 cos of 2 pi by a x. Now this momentum operator p of x is simply minus h bar dou by dou x. Let's remember this. Okay, you must have seen how it was derived for a plane wave solution, how we got this to be equal to minus iota h bar dou by dou x. It was given in the lectures. Okay, so it is simply minus iota h bar dou by dou x root 3 cos of 2 pi by a x dx. Okay, so now let's just insert another slide. root 3 and root 3 will simply make it 3, and this also has a 2, so we will simply say this is equal to minus iota h bar 3 minus a by 2 2 plus a by 2 cos of 2 pi by a x, and the derivative of this thing is simply 2 pi by a minus sine of 2 pi by a times x. It is simply minus 2 pi by a times sine of 2 pi by a x dx. Okay, or simply this is 2, this if we take this outside the integral, so this is a constant, it will be simply 6 times iota h bar pi by a minus a by 2 to a by 2 cos of 2 pi by a x sine of 2 pi by a x dx. Now we know that sine of 2 theta is 2 times sine theta cos theta. We can clearly say that this is equal to, this integral is simply equal to 6 times iota h bar pi by a minus a by 2 to plus a by 2. This is now sine of 4 pi by a x dx. Okay, by 2. Now we know that sine 4 pi by a is an odd function. Okay, since it's an odd function, therefore minus a by 2 to plus a by 2 sine of 4 pi by a x dx is equal to 0. Thus the average momentum value is simply equal to 0, because the value of this integral is 0. So it simply means the option A is the correct option to go with. Now let's move towards another problem which is associated with the lattice structures, and you must have gone through the week 2 lectures, where in the week 2 lecture professor at the end of the lectures he just showed you how we obtain the lattice different type of crystal structures, and in 2D material systems we will be having 5 different types of lattice structures and crystal lattices, and in 3D how we will be having different kinds of let's say cubic body centered cubic and face centered cubic uh, cells, and the professor taught us about three cubic cells, which was the face-centered cubic cell, body-centered cubic cell, and this simple cubic cell. And now, in this problem, or in this next part of the assignment solving or problem solving, what we will do is we will solve the same thing, the uh, uh, for the silicon atom. As we know, the how is a silicon atom, what does it comprise of, what is its unit cell kind of. So actually use the unit cell of silicon is known by the name of diamond cubic. Okay, diamond cubic. It is known by the name of diamond cubic. Basically, it it comprises of two FCC unit cells. Okay, it comprises of two FCC unit cells. Professor taught us about the crystal lattices, how we can obtain the reciprocal lattice vectors, etc. But in this problem, what we are going to first see is we are going to see how orienting the material, any material, along a particular plane. Let's say, for example, if I have a silicon, I will be having planes for this. By plane, I mean I can orient the silicon. For example, in my channel, if I am making a transistor out of the silicon, I can orient it such that the transport is happening along the x direction, let's say only, and the x direction plane, let's say it is 100 plane. Okay, and we are just considering the transport or the movement of the carriers along this 100 plane. We are applying the bias at the source and the drain, and sorry, at the drain side, keeping the source constant, keeping it grounded. And when uh, when we apply the gate bias to this device, we will be modulating the concentration of the carriers in the silicon channel. So the concentration of the carriers is largely determined by the orientation of the silicon channel material itself. For example, a plane, let's say 100 plane, will have a particular number of concentration of atoms, and the atomic density or the concentration in the another plane, say 110 plane, will be different. So the carriers will respond differently if a channel is oriented along one direction or if a channel is oriented along another direction. So it is essential to uh, to keep the track of the orientation of the channel as well, because the defect, you must have heard that, for example, whenever we make a transistor, there are some defects associated with it. There are fabrication defects, etc., and those defects also depend upon the atomic density of the channel material itself. Okay, so this silicon, basically, let's concentrate on its unit cell first. So the silicon basically consists of two FCC unit cells. Okay, it consists of, let me write it down, two FCC unit cells. Let me write it down like this: two interpenetrating. Okay, two interpenetrating FCC unit cells. Okay, and one FCC unit cell, if it is, for example, at its located at x equal to 0, its one corner point is located at x equal to say it is centered or located at what we can say at the origin of the coordinate system, because the coordinate system what we choose is in our hands, and another FCC lattice will be displaced from the previously taken FCC lattice by quarter in every direction. Okay, so by quarter, what I mean, the second FCC, if this is the position of the FCC, first FCC lattice, the position of the another FCC lattice will be displaced by quarter, quarter, and quarter for the second FCC lattice. This is the first, this will be the second FCC lattice. So basically these are two interpenetrating FCC lattices that we are looking into when we are forming this silicon unit cell. So it is what we are going to look here You can clearly see in this diagram over here that we are having this silicon unit cell over here. This is a cubic unit cell. Okay, this is a cubic unit cell with the atoms, 8 atoms at the 8 corners and 6 atoms which are at the faces, which are shared between the two. And apart from that, we will be having 4 atoms which will be lying within the unit cell. Okay, okay, these are the 4 atoms which are lying into the unit cell. So if we are going to find how many atoms, silicon atoms, are present in one unit cell, we will simply say they there are 8 atoms for a silicon unit cell. There are 8 atoms at corners, and they are shared between 8 cells. Similarly, this is one. Similarly, we will be having 6 atoms at the faces, and they are shared between 2 cells. Okay, and we will be having 4 atoms within the cell. So the total number of atoms is simply 8 into 1 by 8 plus 6 into 1 by 2 plus 4. It is 8. So the 8 atoms in sorry in one unit cell for silicon. Okay, now what we are going to do is we are going to uh, look into the information which is associated with the density of silicon. Okay, we will calculate the density of the silicon. If it's Lec constant, we know the Lec constant is given for silicon, it is 5.43 angstrom, and the effective mass in atomic units is 28.085. And now from this we have to calculate the density of silicon for this. Okay, now if we calculate the density of silicon, we have to simply say its Lec constant, which was A, is equal to 5.43 angstroms. Okay, it is 5.43 angstroms. The atomic mass is equal to, let me check it, 28.085. 28.085. It is in atomic mass units. If we convert it to grams, it is 28.085. It is 1.66 into 10 to the power of minus 24 gram. So let's calculate this. So it is coming out to be equal to 4.622 into 10 to the power of minus 23 grams. So it is the atomic mass of silicon. Now for density, atomic density of silicon is simply the number of atoms in a unit cell multiplied by the mass, okay, divided by the volume of unit cell. This is what it is. Now the volume of unit cell is simply, uh, since this is a cubic, it will be simply a cube, since it is cubic. Okay, since it's cubic, we will be having the volume to be equal to a cube. So if I convert this to the centimeters, this angstroms, it will be 5.43 into 10 to the power of minus 8 centimeter. Since it is cube, it is cubic centimeter. If I now cube this thing, I will be having 5.43 into 5.43 into 5.3, which is 160.103 into 10 to the power of minus 24 centimeter cube. Okay, this is the volume of the unit cell. Now density is simply density of silicon is simply number of atoms is 8. The mass came out to be 4.622 into 10 to the power of 23. 4.622 into 10 to the power of minus 23. Volume came out to be equal to 1.60 into 10 to the power of minus 22. 1 point, sorry, it's 23. 1.601 into 10 to the power of minus 22 gram per centimeter. Okay, so let's use the calculator for this. It is 8 into 4.622 divided by 1.601, which is 2.31, which is 2.31 gram per centimeter cube. So this is the density of the, okay, so this is the density of the silicon. Now we have to find the atomic density, which is the number of silicon atoms per centimeter square along three different planes. One is 100 plane, 110 plane, and 11 plane. Okay, first if I take this 100 plane, if this is my x-axis, okay, this is the coordinate system. This is x, this is y, and this is z. Okay, so it means that this is our x-axis. Okay, this is x-axis. So the 100 plane means I have to intersect the x-axis only. Okay, so I have to intersect the x-axis. This is my 100 plane. Okay, this is my 100 plane. So this is our 100 plane. So for 100 plane, clearly I will be having these atoms, 4 atoms at the corners, and these 4 atoms will be shared with the other uh, unit cells, and as a result of this thing, this 100 plane, for 100 plane, I will be having in total 2 atoms, 2 atoms in the plane. Okay, I will be having 2 atoms in the plane, and the plane looks like this. the plane looks like this. This is the A, this is A, this is A, this is also A. So in general, what we have is the area of the plane is simply equal to A into A, which is A square, and A is simply 5.43 into 10 to the power of minus 8 centimeters, or simply if I square this, it comes out to be equal to 29.484 into 10 to the power of minus 16 centimeter square. So this is the area of the plane. Now the atomic density is the number of atoms. Atomic density is simply number of atoms divided by the area of plane, area of 100 plane. Okay, so number of atoms came out to be equal to 2, and the area is 29.484. This is 10 to the power of 16 now. Okay, centimeter. Okay. It will simply come out to be equal to, let us do it like this, 2 divided by 29.484, it comes out to be equal to 6.78 into 10 to the power of 14 per centimeter square. So this is the atomic density along 100 plane. Okay, 100 plane. Similarly, now we have to look for the atomic density along 110 plane, and I have just put the image over here for the 100 plane. 110 plane simply means that I have to intersect the x axis and I have to intersect the y axis as well using my plane. So this is the plane, this is my plane. Okay, this is my plane, right, going right through this diagonal, which is this. If we consider this face, this as a one of the face, is this is our plane. So it simply means that if this is A, this is A, then the one of the side of the plane will be having the length of A square plus A square equal to root 2A. So this will be equal to root 2A for this 110 plane. This is what we have written over here. It is root 2A. Okay, root 2A, and this is itself equal to A. So this is itself equal to A. So how many atoms will it be having? So first of all, it has the 4 atoms at the corner, which are shared with other 4. So as a result of this thing, we will be having just 1, and this also has 2 atoms at the face. Okay, these 2 atoms at the face are shared between 2 other, let's say another neighboring unit cell. So as a result of this thing, we will be having 1 atom, and for this we will be having 1 atom per unit cell. And also because of those interpenetrating FCC lattice, we had 2 interpenetrating FCC lattice, and because of that second interpenetrating FCC lattice, we will be having 2 atoms. Okay, so as a result of this thing, we will be having in total 4 atoms for 110 plane. Okay, for 110 plane, We now have 4 atoms. Previously, for 100 plane, we only had 2 atoms. Now we are having 4 atoms. So the atomic density is guaranteed to change because the area of the plane has also changed. So let us write down the area of 110 plane. It will simply be equal to, this is root 2a times a. This is root 2a times a is root 2 a square, which is simply root 2 times 5.43 into 10 to the power of minus 8 whole square. Okay, and let's solve this. It is 5.43 into 5.43 into root of 2, which comes out to be equal to 41.6979 into 10 to the power of minus 16 centimeter square. So the area of the plane has also changed. That's what I was talking about. Whenever we change the plane, or whenever we orient the silicon along some different plane, we will be having different atomic densities. Not because only the number of atoms is changing in that plane, but also because of the area of the plane is also changing. So the atomic density is for this 110 plane is simply number of atoms divided by area of this 110 plane. So it is 4 divided by 41.6979 into 10 to the power of minus 60. So let's calculate this thing. So it comes out to be equal to 9.592 into 10 to the power of 14 per centimeter square. So this is the atomic density for the 110 plane. Okay. Now moving to the another plane, which is 111 plane. What does this mean? It means that I have to intersect the x, y and z axis at the let's say the 100, 010 and 001 coordinates. Okay, that's what we are doing. We are intersecting. If I consider this to be normalized, we are intersecting the x, y and z, all the planes. Okay, so if I intersect these planes, I will be having the atoms, number of atoms which look like this. For example, I will be having this atom at this corner, this half atom, this half atom over here, this half atom over here, and this atom, so in general, what we are having these three half atoms, and we are having 3/1/6 of atoms. Okay, which will be shared between rest of the 6. Okay, and as a result of this thing, this 111 plane has two atoms. Okay, now just a second. Now the area of the plane, area of the plane needs to be found out. So the area of the plane is simply, this is, okay, uh, Swayam, you have raised your hand. Uh, if you have query, please ask. Okay, might have happened by mistake. If not, then you can unmute and ask, or even you can type in the chat. Okay, no issue with that as well. So this is A, this is also A, then this diagonal which goes through this face diagonal will simply be equal to a square plus a square, which is root 2a. Okay, it will be equal to root 2a. Similarly, this will also be equal to root 2a. This will also be equal to root 2a. Okay, now we have to find the area for this triangle. We will draw the perpendicular bisector over here, and as a result of this thing, we will be getting something like this. This is the triangle. Okay, this, since this whole thing was root 2a, now this is the half of that, and we will be having root 2a by 2, and this whole thing is root 2a, okay, which remains as it is. So it simply means that we have to find this hypotenuse, sorry, this perpendicular bisector which we drew on this plane. So it will simply be equal to this root 2a whole square is simply equal to root 2a by 2 whole squared plus this perpendicular square. Okay, this is simply equal to 2a square minus 2a square by 4. Okay, this will be simply 2. Okay, this is L square, or simply this is equal to 4 minus 3. This is simply equal to root 3 by root 2a. Okay, this is what we have written over here. Let me write it clearly again. Sorry for this. So it will simply be this L, this perpendicular, is simply equal to 3a square by 2, or perpendicular is equal to root 3 by 2a. That's what we have written over here. Now the area is simply of this area of this plane is simply equal to 1/2 of this base, okay, 2a by root 3. This is the base, root 2a by 2, root 3a by root 3 2a, and multiplied by 2, because this was the area of this triangle. Okay, since these two are symmetric, we have to multiply by 2. So this 2 and this 2 will go, and this root 2 will go with this root 2, and the area will simply be equal to root 3 by 2 a square. Okay, so that's what we have calculated over here, and it comes out to be equal to 25.53 into 10 to the power of minus 6 centimeter square. Now the atomic density atomic density for 111 plane. Okay, for 111 plane is now simply equal to number of atoms divided by the area of this plane, area of one plane. Number of atoms was number of atoms was 2. Okay, so it is 2 divi divided by 25.53 to 10 to the power of minus 60. Or simply, let's divide this. It comes out to be equal to 7.834 into 10 to the power of 14 per centimeter square. So what we have found out, that each atomic plane has different atomic density. Say for one plane it is approximately 7.9, for 100 plane it's approximately 9.6, and for 100 plane it's approximately equal to 6.8. So clearly this 110 plane, it has more atomic density. Okay, atomic density is more in case of 110 plane as compared to the rest of the planes. So uh, if you have any question till now, uh, you can please unmute and ask regarding the problems we solved today. If you have any question, you are free to ask any question. You can type in the chat, or you can even unmute yourself. So what we have deduced from this problem is that if I orient the silicon channel along a particular direction, I will be having different response from the silicon material itself. For example, when I am applying some gate bias to this channel, which is oriented along, let's say, 100 plane, the carriers will respond differently as compared to the 110 plane because of the different atomic densities in that plane. So this is one of the key takeaways from this problem. You can say that clearly we can have different uh, responses of the different planes in response to the different applied biases. Okay, because of the different concentrations that correspond to that particular plane we are studying, or we are orienting our channel along. Okay, so uh, if you have any question till now, you can unmute yourself and ask. Meanwhile, I can have some water. Okay, I guess there is one question from Mr. Ramaya. He says that what could be a suitable reference textbook for this course? Okay, so as professor must have told you about the books that you should follow, you can furthermore ask on the forum as well. But what I would suggest is that if you will need, I would say you would need to follow 2 or 3 books for the whole course, and which will help you gain insights. Let's say for the uh, starting of the course, let's say for the quantum mechanics, leaving quantum mechanics aside, for the rest of the starting course, you can take help from the standard simple books like Donald A. Neiman. And for getting a bit more insights, you can go and check Robert Parrott as well. Okay, if you want to check the quantum mechanics part as well, you can check. There is another part for the same book, the Robert Parrott, which is the advanced one, and it deeply talks about the, not deeply, it talks about the quantum mechanics as well. So what I would say, if you are considering the initial part only, then these two books are good to go, I guess. Donald A. Neiman and Robert Parrott. And there are also some good books which you can follow. These two are also good. I'm not saying that they are not good. They are really good books. But you can follow the SMZ's book. You can follow for the more advanced concepts, Ashcroft and Mermin. You can follow Charles Kittle. Okay, these are all the books you can follow uh, for the course, and not only for the course, for gaining more insights into the course as well. But what I would suggest ask this question in the forum as well, because uh, the professor can tell you much more. He can tell you in much more detail, and he has far wider knowledge and uh, far wider insights than me, and he will be able to provide much more rigorous information regarding the selection of the books as well. So I would suggest start studying Donald and Neiman and Robert Perret for the initial part of the course, and then as you go on to the circuits, uh, there are advanced books from like we can say, not advanced, you can say that there are books from the Professor Behzad Razavi. You can check those books, and uh, that's all with what I can say. But I would suggest you to ask this in the forum, and that will be much beneficial for you. Okay, one more thing I would suggest to you. I would suggest, if you want to build some good concepts about the device physics, you should solve the problems from the robot parent. Okay, it will help you a lot. Uh, that book is really good for the basic understanding, and you will never forget anything whatever you learn there, because you will solve the problems, and the problems are oriented in such a way that they will uh, brainstorm you sometimes. Okay, so uh, do we have any other question regarding the lecture or the problem solving session today? Otherwise, if we have no questions about today's session, we can end this session, because we will be having another session from 5 to 7, I guess. Yes, it's from 5 to 7, where another TA will solve the problems, and he will also provide you insights about the course. So if you have no questions to ask, we can end the session. But if you have some questions, then you can stay and ask those questions in the chat, or even unmuting yourselves. So I guess let's wait for a couple of minutes. If there are no questions, we can end the meeting. Sir, what could be a successor course to this course as a next step? Okay, about if you are asking from the NPTEL platform, I cannot suggest much because this is a vast course. This course deals right from the basics of quantum mechanics, then moves to the device physics, and then goes to the circuits. So this is a relatively vast course. It gives you insights about the whole things that you are going to require. So if you want to be specific about any course, let's say you want to go to the device physics itself, so I have to check with the NPTEL course sheet which will be the best course for you. For example, if we just go for the device physics, although the content taught in this course is enough for you to build upon and go through the advanced books, and because the course is designed by the professor in such a way that you get all the insights that you require, mostly about the device physics. So if you are going into the device physics, I would say that you do this course, solve the problems from the Robert Perret, that will be very beneficial for you. Then go to the advanced books like Charles Kittle and Ashcroft and Mermin, and you will also SMZ as well, because you will need some practical aspects as well. You will get some deeper insights about the device physics. So these three books, after doing this course, or simultaneously when you are doing this course and simultaneously start reading and solving the problems in that book, in these three books, yeah, I would say that you will be doing wonders in the field of device physics. But I would suggest starting with the Robert Perret itself. Okay, Robert Perret is a really good book to go with these kind of concepts. Okay, so if we have no questions, I request you to leave the meeting, or I will end the meeting from my side itself. Okay, so I am going to end the meeting. Thank you for joining the meeting. And if you have any queries, you can even ask me through my email. You can just drop an email, and I will be happy to respond to your queries. Thank you.